Yes, I begin. So the first thing we need to add to what we did last time to discuss is the case when M actually is a manifold with a boundary. Also compact manifold, but having a boundary. Then the question arises, how to define a Morse function? What it is? And something is obvious. Boundary or not, a function has critical points, including boundary points. Partial derivatives are defined also at the boundary points. So first, certainly we assume that all critical points are non-degenerate, which means, in particular, there are finitely varying critical points. Non-degenerate. Also, we can assume that the boundary points are not degenerate for the whole function, for the function on M. That is, that at every point on the boundary, the partial derivatives with respect to the local coordinates around this point, at this point can be all zero. These assumptions are sort of natural. But then something should be assumed regarding the restriction of the function to the boundary, also a function, on a manifold of dimension n minus 1. What would you think the most natural? I ask because I see two possibilities, and it is not clear immediately which is better. So the restriction of the function to the boundary, it is, you understand, a function on an n minus 1 dimensional manifold, and as such it can have critical points. I mean, not the function of the whole manifold, but on the boundary. And there are two competing possibilities. You don't want to say, then I will say. The first possibility, which may seem more natural, that you can assume that the restriction of this function to the boundary is also a Morse function of the boundary. There is a good theory about Morse functions or boundary Morse theory with this assumption. But we will consider the opposite assumption. So according to my definition, the function on the boundary should be constant. So the boundary should be a level set. Here actually also some options. If boundary is not connected, then do we really need to assume that the values on different components are the same? A constant actually is a function with zero differential. So a function, it is natural to assume that it is constant on every component of the boundary. Do we need to assume that these values on the components are the same? Again, there are options. For my purposes today, I don't want to consider other options, although they may be important in some parts of differential topology. So, my definition, a function on a manifold with a boundary is called a Morse function if 1. All its critical points are non-degenerate, I mean the whole manifold. Second, no critical point, again with respect to all whole manifold, on the boundary. Third, the value on the boundary is, the restriction to the boundary is a constant. It is certainly up to us to give definitions, but we have a theorem that there exists a Morse function on any compact manifold without boundary, and we even have several proofs, at least two proofs. So now I want to extend the proof to this case. So again, a Morse function on a manifold with a boundary is defined absolutely as usual, plus no critical points on the boundary. I mean the whole function, not its restriction to the boundary, but the whole function doesn't have critical points on the boundary. And on the boundary, the value is a constant. I can say that for our purposes, and I will give it a construction of such a Morse function immediately. For our purposes, it is natural to assume that the value on the boundary is maximal. That is, on the boundary it is equal to some constant c, and everywhere in the interior of the manifold, the values are less, strictly less than c. So, and in the construction which I'm going to present, the c will be 0. So the function will be 0 on the boundary and strictly negative inside the manifold. Again, it is not the only possibility. There are other possibilities which I will not consider because I cannot consider everything. So, fact 1 exists. There exists a Morse function, according to the definition, on a manifold with boundary, compact manifold with boundary. The fact 1.5 is that actually the proof is the same as before. If you don't remember the proof, then you will sort of see it again, although I will not go into details. So, M is a compact manifold with boundary. Yeah. And I want to construct the Morse function as I defined it. You remember how we, or don't remember, how we proved this existence theorem in the boundary-free case. We first considered an arbitrary function, for example, 0, but not necessarily. And then we also considered atlas, covering of the manifold by neighborhoods with coordinates. Actually, the domains of these charts supposed to be the whole space Rn. And actually, the images of unit balls should cover M. And then within every chart, one by one, we modified a function using some lemma, and in this way, we could obtain a Morse function on the whole manifold, which was, with all derivatives, as close as you wish to the initial function. Now the initial function. I want to consider a function which is 0 on the manifold, on the boundary, and strictly decreasing in the direction inside the manifold. We had this construction when we constructed a thing which I call the color. So this is the M. This is the color, which now I assume to be directed epsilon is positive as usual. So this direction to the negative values of parameters. And then simply the projection of this is a function without critical points, absolutely, because the gradient always directed down. And then we extend this function to the whole manifold, as usual we do. All values there are negative. This is the first step of the construction. Then it is not. It has no critical points here, so it is constant on the M, so something is satisfied, but not all. Then we do the following. We consider charts of our manifolds. So phi I n dimensional manifold into M, and I suppose actually that it is into the interior of M. So these charts, not these charts, but phi I of the ball of radius 1 cover cover what? Cover M minus a color, minus a part of a color, say minus dm times this. Do you understand? And this capital N, I have found many charts. So it looks like this. Then what I do, I also suppose that this union, well, actually every image of the ball of index, excuse me, it's better to write here 2 epsilon over 3, because I want to say that this is contained in this bigger set. So I have finitely many charts, and then I use a lemma which I also used in the absolute case, boundaryless case. You remember that if you have a function on a ball, so there was a lemma. We have a function, say f, on a ball. It is a smooth function, but not necessarily more smooth. It may have degenerate critical points. But then there exists an open dense subset U in Rn, so that for every A in U, the function fa, which is f minus the dot product with A, such a linear function, a1x1, and so on, an xn. Such function is a Morse function. A can be chosen as close to 0 as you wish. U is in dense open subset. And this gives us all, because we take one by one. You remember, I just remind the proof which we discussed here. We take one by one these charts. Phi I of d1, phi I of phi 1 of d1, phi 2 of d1, and so on. And then we enhance our function within these sets without spoiling it, where it is has been always enhanced. We take the sets, and in every set we replace the function f by fa, where a is very close to 0. And then we make it equal to f in the complement of phi I of d2, using the function you remember, which is equal to 1 on the ball of radius 1 and is equal to 0 outside of the ball of radius 2. So this standard construction, we discussed it here, and it is, again, you can find the proof in my notes if you don't remember, shows how to make a function a Morse function. We do not do anything with our function in some neighborhood of the boundary. So at the boundary, it is as requested. It is constant. It is 0 actually in this construction, and has no critical points in some neighborhood of the boundary. So this is how it is proved. Questions? Well, a proof is a proof. It's always difficult to fully understand the proof when it's just shown on the lecture because of all this hand waving and pressure which I apply to you, constantly saying that it is very obvious. But it is written so you can look through the proof in a written form. This is one thing. So this is a Morse function on the manifold with boundary, and now I want to say that my theorem, which was proved last time, can be applied to manifolds with boundary without any changes, either in the statement or in the proof. So the boundary case of the main theorem we have a Morse function f as before. It is negative everywhere in the interior of the manifold, 0 on the boundary, and so on. And then we consider the sets m less than or equal to c. And what I said last time remains true, that if the c prime is less than c double prime, and there are no critical values in the interval, closed interval c prime c double prime, then m less than or equal to c, c prime are diffeomorphic, the same. If there is a critical point, just one critical point between if critical and no more critical values between c prime and c double prime, then m less than or equal to c double prime is obtained from m less than or equal to c prime by attaching a handle of index equal to the index of the critical point. And that's all. Simply we move and move, and the manifold m less than or equal to 0 will be our manifold. So manifold with boundary also can be obtained from nothing, from the empty set, by successive attaching handles. Simply the final result will not be a closed manifold, it will be a manifold with boundary, otherwise it is the same. So it is done. Questions? Dale, you are my last hope, no? No. Then, to finish with the Morse theory, also it is actually very rich. I cannot avoid saying one thing. No secrets from friends. It is one of my principles. Actually, Morse theory is not for finite dimensional manifolds. Morse himself considered it having in mind not manifolds which we consider, but mostly manifolds of smooth curves. The function, I can say that it is the length. Actually, there is some other function which is called energy, which is more or less, well, close to, by meaning, to geometrically to length. And we don't need that the manifold is finite dimensional. All we need that the manifold, that the sets m less than or equal to c are compact. And then everything is the same. Everything is the same. And traditionally, the Morse theory is applied to manifolds of curves, of smooth curves, of closed curves, and the critical points are geodesics. So this is actually a theory which is applied to geometry, to finding geodesics, to proving that they exist, and so on and so on. The finite dimensional version of the Morse theory from the point of view of Morse is a toy. But still in topology it becomes very important. Maybe Morse even did not fully realize what kind of an animal he actually killed by this theory. Now I want to discuss, to finish with more theory. You can read books. Again, I can refer to the wonderful book of John Milner, which is called The Morse Theory, and written in the early 60s. Still, maybe this is the best source of this theory. The book is short, which is 200-something pages, which makes it even more attractive. And I here only will present the way how to obtain from the Morse theory full or partial classification of manifolds of small dimensions. And I begin with dimension 1. Actually, there was an exercise in my list of exercises, and some of you did it. So I'm not sure that you will be surprised by the result, but you may appreciate the way how it can be obtained. Since I consider compact manifolds, I formulate the result for compact manifolds, but maybe with boundary. So a connected compact one-dimensional manifold is either a closed interval or a circle. Which means that disconnected, if you drop the condition of connectedness, then it will be a disjoint union of some amount of intervals, some amount of circles. Let us prove it. So again, I consider a Morse function of my manifold. If it is a boundary manifold, then D manifold, then I assume what we did today. And I consider, so it can be obtained, according to the Morse theory, from nothing, from the empty set, by attaching handles of index 0 or 1, because indices are always between 0 and the dimensional manifold. So, what is a handle of these two indices? Index 0. We have an embedding of S negative 1 times d1 into dm, but this is empty. So this is nothing. And then we attach d0 times d1, simply an interval, and we attach it to the empty set embedded in the boundary of the existing manifold, which means simply that we add this interval as a new component. Index 0, index 1. We consider the product of S0 and D1, which is S0 and D0, which is just a pair of points into the boundary of M. M is one-dimensional. So we choose 2 points on the boundary. Different. It's an embedding. And then we attach again a disk, D1 times D0, to these 2 points. So my manifold is obtained from nothing, from the empty set, by a combination of these 2 operations. Just draw a new interval, that's okay. Or choose 2 points on the boundary of the existing manifold and draw and add, attach an interval to these 2 points. Okay? Now let us look what can happen. Not necessary, but I want to say this. What happens on the first step? We have as an empty set, nothing. And we want to attach an interval. There are no 2 points, no even 1 point on the boundary of my manifold and in the manifold actually. So we can attach only, we can make only the attaching of the first kind. So after the first attaching, my empty set becomes an interval. Now let me assume that at some step after some amount of attaching handles, I get a manifold which is a union of intervals and circles. So suppose that MC prime, M less than or equal to C prime, is this: several intervals and several circles. Then what happens when we make a transition is MC prime. Make a transition to M less than to C double prime. 2 possibilities. The first is that we take this and attach a new interval as a new component. Certainly the manifold remains the same. The amount of intervals becomes bigger, but again, a union, disjoint union of intervals and circles. Now here, we should choose 2 points in the boundary. And there are, again, 2 possibilities. These 2 points may belong to the same component or to different components. If to different, then we attach this. And what happens? We get a new interval, and just the number of intervals becomes one less. What if they belong to the same component? Then one interval becomes a circle. And the theorem has been proved. So if we had some amount of intervals and circles, then after attaching a handle of any of these two kinds of handles, the manifold remains a union of intervals and circles, although the amount of those may become different. This 3 actually cases, not 2. We see that what happens in every case, shown at the picture. Always dimension 1. If you do not have questions regarding this theorem and the result, but if you have questions, then please give them to me. I appreciate your questions. Doug. Virgil. No. Patrick.
What's the third case?
The third case, we attach an interval to 2 points on the boundary of the existing manifold. And if these 2 points belong to the same interval, same component, then we have 2 intervals attached to each other by their endpoints, which is a circle. You should not, this picture may be slightly misleading because on my picture this is not a smooth curve. But you remember that this attaching can be always made in the class of smooth manifolds. We discussed it. So just one of the intervals becomes a circle. And why not? Why not? Why not? Now, dimension 2. And let me first ask you a funny question. Very funny question. Do you know some two-dimensional manifolds? Yes. Wonderful. Which ones? You begin with sphere, yes. Very, but please do remember that certainly it is reasonable to consider connected manifolds and compact, because disconnected manifolds can be obtained from, as they are just the joint unions of connected manifolds. So connected, compact, two-dimensional manifold with or without boundary. And example, just chronological number 1, a sphere. Okay, more? Projective space. Somehow you avoid sort of simplest examples, but I buy this. The projective plane, two-dimensional. What else? You avoid manifolds with boundary, but there are manifolds with boundary. Some of them are very simple. Square, well, I prefer to say disk, because square somehow, the picture is misleading. It seems to be certainly the same, but seems to be not smooth. A disk, a manifold whose boundary is one circle. More? Actually, frankly, I expect to have 2 more examples. Huh?
Yeah, what's the torus?
Torus, yes, but it is not within my set of examples. Which torus, yes. There are examples sort of more elementary. No, don't want to say. Möbius bend. The standard Möbius bend, you can do it make it out of paper strip. You know what it is. It's important to know because I will use Möbius bends. It is a manifold, very much two-dimensional, and its boundary is a circle, one circle. And one more example, which some people would have named first, is the celebrated Klein bottle. Klein bottle. So there are some examples. My classification should embrace all these cases, including this torus of yours. Very interesting. Now, I want to specify geometrically some operations, some constructions which can be used to obtain a two-dimensional manifold from a two-dimensional manifold, with or without boundary. I will not really, well, the boundary case is okay. So there are three standard operations and one, how to say, sort of less standard. But let me begin with three standard operations which can be applied to two-dimensional manifolds. First, drilling a hole. Just imagine that you have some two-dimensional manifold with a piece of it, and just at some place you delete a small coin. Then we obtain a new manifold, new two-dimensional manifold. Its boundary, compared with the boundary of the manifold which existed, its boundary has one more component. Actually, a boundary over two-dimensional compact two-dimensional manifold is a compact one-dimensional manifold without boundary. And according to our previous result, it is a collection of circles, no intervals, without boundary. So this is one operation. Two more operations, actually three, but the last one will be sort of complementary. Second, you know, in here, we are not the first to encounter this difficulty. It is terminological difficulty. We simultaneously consider two things. Morse theory, where attaching a handle is what we call attaching a handle. And the two-dimensional topology, where attaching a handle has a different sense. I hope you will not be very much confused with this. Attaching a handle. You consider a manifold. You drill two holes, after which you attach such a tube, a handle, empty inside. You understand? This is what is usually normally called attaching a handle in the two-dimensional topology. And the operation number 3 is geometrically not so appealing, mostly because it is sort of impossible to do it within this three-dimensional space, which we usually use for pictures. So, attaching a Möbius band. We have two-dimensional manifold. Again, it is big, it's just a piece of it. We drill a hole, and then we consider a Möbius band. See it? If you prefer, I can make this picture also Möbius band. We consider a Möbius band, and the boundary of this Möbius band is a circle. One circle, not two circles, right? So we take this circle and take the boundary of the hole which we have just made, and we attach this Möbius band to this hole. It is not possible to do it within the space R3 usually, at least without self-intersections. So you should somehow exploit your imagination. I can say the following, how it is done. We take this hole, just imagine that for every two opposite points, we attach a diameter. And we do it for every 2 points, but when we come back to our initial position, then we will not be able to attach it to this. So it again can be done only in the space of dimension more than 3. But still, it is possible to say that this Möbius band, which we attach, consists of all diameters of the disk which we delete, which are supposed to be disjoint. This disjointness cannot be achieved in R3. Do you understand this construction? So this is the most complicated construction.
So
Yes.
if you have a sphere, can you get a Klein-Bottom by doing these combination of these three operations?
Klein-Bottom?
Yeah. So you start with a sphere, a two-dimensional sphere.
Yes. Certainly I will do that. But if you ask Patrick, I can send immediately. You take the sphere and do this twice. Attach 2 Möbius bands. And you will get your beloved Klein-Bottom. If you take a sphere and attach 1 Möbius band, then we are in Duke's domain. We get a projective plane. I do not ask you because you don't know what happens if we attach 3 Möbius bands. Now, well, I want to formulate a certain result. Simply because obviously I will have to return to it next time. But I want that you have this result, and maybe you have a temptation to come next time and to look how it is proved. Statement: every compact two-dimensional connected two-dimensional manifold can be obtained from the sphere, or if you wish from the disk, or if you wish, but from the sphere it is more convenient. Coming from the sphere by drilling some amount of holes, attaching some amount of handles, and attaching some amount of Möbius bands. Absolutely arbitrary. And as I said, for example, Klein-Bottom can be obtained from a sphere by attaching 2 Möbius bands. You can ask very natural question to ask. So these manifolds, we can call them classical two-dimensional manifolds or classical surfaces, are characterized by 3 numbers. We have a sphere, no numbers. We have some amount of holes, say 10 holes. 10 is a number. We attach some amount of handles, say 5 handles. 5 is a number. And we attach some amount of Möbius band, say 7 Möbius bands. What we get is a classical surface, and the statement which I have already formulated is that every connected, compact, two-dimensional manifold can be obtained, is diffeomorphic to one of these classical surfaces. But now the question which you should ask: are these 3 numbers fully determined by the manifold? Is it possible that we have 2 spheres, this and this? Then we drill holes here and here, we attach handles, and we attach Möbius bands. if we have a diffeomorphic manifolds, does it mean that the number of holes, the number of handles, and the number of Möbius bends on the two sides are the same? What do you think about that? You don't. Why you don't think so?
I think like attaching multiple Möbius bands.
Attaching?
Like if you attach 3 Möbius bands, that would be the same.
You know something. I understand. So first of all, number of holes is something which is fully determined by the topology of manifold, because this is the number of components of the boundary. So if two manifolds which are obtained to classical surfaces are diffeomorphic, then a certain number of holes is the same. And yes, Dale formulated a relation. If you attach 3 Möbius bends, it is the same as to attach 1 Möbius bend and a handle. So actually, you should never attach more than 2 Möbius bends. Because if there are 3 of them, you just replace this combination by 1 Möbius bend and a handle. So actually, my theorem, after we prove this result, I will not do it today, but it is true and very geometric, shows that every manifold, two-dimensional compact connected manifold, to the every compact surface, compact connected surface, is diffeomorphic to a manifold which is obtained from the sphere by drilling H holes, attaching G handles, and M Möbius bend. And this M can be always, we can always assume that M is less than or equal to 2, 0, 1, or 2. And then next result, that if we impose this condition that M less than or equal to 2, then all the surfaces are pairwise not diffeomorphic to each other. We can formulate it differently. I say this, and we stop today. The proof is, as usual, we just apply the handle construction, the Morse theory, and we have this after we consider all possible cases. There are more cases than a one-dimensional case, but still they can be all considered. But now I want to say, let us begin this attaching with Möbius bends. 0, 1, or 2. If 0, no Möbius bends. Then we take just a sphere, drill holes, and attach handles. It is one possibility. 1 Möbius bend. As I mentioned, if you attach 1 Möbius bend to a sphere, it is a projective plane. So you take a projective plane, drill holes, and attach handles. 2 Möbius bends is a Klein bottle. So we have Klein bottle. Again, we can drill holes and attach handles. So we can say this in different form. Every compact connected surface is diffeomorphic to a sphere, a projective plane, or a Klein bottle with a certain amount of holes drilled and certain amount of handles attached. And this is all. The proof, direct application of the Morse theory, which I will do next time. Today, thank you for your attention.